All right, so let's talk about simple harmonic motion and the important things you need to know. I'm going to first start by talking about the graphs. Okay, so first we're going to start with a position graph. And let's go over a little bit of the vocabulary. So we have already talked about period, which we have used the capital T, and the units for that are seconds. Okay, and then we talked about frequency. Frequency is a lowercase f, and we use the units of hertz or seconds to the -1. And for this, we need to talk about amplitude. Okay, amplitude for simple harmonic motion. You'll sometimes see it as an A, or sometimes it'll be an X. Okay. And this is going to be measured in meters. So A or X, it's going to depend on the problem that you're working on. So use whatever they give you. The period, to define it, is the time for one cycle. And frequency is the number of cycles in 1 second. So we've already talked about these. And we also talked about the relationship between period and frequency. So period is the inverse of frequency, and frequency is the inverse of the period. So we're going to add on that in a moment. We're also going to talk about how we talked about wave speed before. So let me go to a different page for that one. And we said it was, sorry, not wave speed, because we're in AP Physics C. Periodic motion, we talked about how you could get velocity by taking 2 pi r over the period, or angular velocity by 2 pi over the period. Well, we're going to go back to this relationship here, only we're going to refer to this as angular frequency now. So if you want to see why that is similar, I did post the Google slideshow that I went through last year during one of the Canvas conferences, and it'll show you how periodic motion is related to circular motion. So again, we're going to call this angular frequency now. So for angular frequency, it is just a W, just like angular velocity, and it's measured in rads. And just like I said a second ago, where we said angular velocity was 2 pi divided by the period, well, we can say angular frequency is the same thing. This can also be rewritten as 2 pi times the frequency f, okay? So we're going to go back to that because I'm going to show you where the equations for the period comes from, and we're going to derive that using those relationships. But we're going to do that in a little bit. Right now, we're going to talk about these position graphs and then the equation for these. All right, so the position graph is not always going to be cosine. It's going to depend on where your graph starts. So for this graph, my graph is starting on the line. So the equation for this position graph, and I forgot to put the M over here for X max. Your amplitude is maximum displacement from equilibrium. And equilibrium is also called the rest position. That's just your 0 position here, okay? So these are your maximum displacements from the rest or equilibrium position. And since this is on the line, this is a sine graph. And then it's going to be the sine of the angular frequency times the time, okay? If we were using A for amplitude, we would write the equation as the position is equal to A for amplitude times the sine of the angular frequency times the time, okay? In order for this to be a cosine graph, it would have to start not on the line. So anywhere other than on the x-axis, which is what I'm referring to as the line. So the equation for this graph would be the amplitude times the cosine of the angular frequency times time, because this is not on the line. Okay? Whereas the one we did previously is on the line. Okay? If you are given a graph and you have to get the period from that graph, the period, again, is the time for one cycle. So from this maximum displacement to the next maximum positive displacement, or one complete cycle is from rest up to a maximum displacement, back to rest, down to the negative maximum displacement, back to rest. Okay, that is one period. And then your amplitude is this maximum displacement here. Okay, that would be your amplitude or maximum displacement. All right, if I was measuring it here, it would be from the rest to that maximum displacement from rest. That's your amplitude there, okay? Or the maximum position away from the rest position, okay? All right, well, we're going to go on ahead and do the velocity time graph, because there are times you have to match graphs or you have to transcribe graphs. So let's talk about how we get to the velocity from the position. So velocity is the derivative of the position with respect to time. So we would just take the derivative of that previous equation. So what I get for my equation here is now angular frequency times the amplitude. And then the derivative of sine is cosine, and then in the parentheses is still just your angular frequency times the time, okay? All right, so then you can look at the graph up here. So if I look at the slopes, because that's the other way I can find velocity, is the slope of the xt graph. If I look at the slopes here at these maximum displacements, I have a slope of 0. So every time I have a maximum displacement, I have a 0 velocity, okay? Now I can look here. I have a positive slope there, which means I'm going to start with a positive velocity. That positive velocity is going to be somewhere that's not 0. Remember, this is 0, and these are positive and negative. I didn't write those in. I'm assuming you got that. All right, so this is positive direction slowing down. So that velocity is going to be going towards 0. Now I get into a negative slope, or a negative slope, which means I'm going to be in a negative velocity. I'm going to go to the negative maximum velocities. Your maximum velocities are going to be at all of these spots where the position graph crosses equilibrium or the rest position. So that means here I'm going to have another positive maximum velocity. And so my velocity graph is going to look like this. Something like that. Okay? All right, well then we can go from the velocity graph to the acceleration versus time graph by looking at the relationship between acceleration and velocity. So acceleration is the derivative of velocity with respect to time. So my equation for acceleration becomes the angular frequency squared times the amplitude times the sine. But the derivative of cosine is the negative sign, so I have to have a negative out here. Let me fix that so it looks a little prettier. I kind of crammed everything in there and did not leave room for my negative sign. All right, so we're going to do exactly the same thing we just did a second ago, and everywhere this is at a maximum, if I look at the slopes there, not that last one, that isn't even at a maximum, that is where my acceleration is going to equal 0. So my acceleration is 0 everywhere my velocity is at a maximum. Now I'm going to look at the slope here. That's a negative slope, so that's a negative acceleration. And every time my velocity graph crosses 0, I'm going to be at one of my maximums for my acceleration. So now It's not a constant change in the acceleration. That was a horrible curve. Let me try that again. Terrible at drawing these curves, as you can see. All right, so your acceleration graph, what it actually ends up looking like is the inverse of the position versus time graph. We can also look at the equation we wrote here, and we can see that part of this is just the graph for the position, which means we can also write the acceleration as the negative angular velocity or angular frequency squared times the position, because this piece of the equation right here is just the equation for the position that we saw up here. Okay, let me use the one with amplitude to be consistent. All right, well, now that we have a graph of the acceleration, if I think about the relationship between net force and acceleration, my graph is going to have the same shape if I were to do a force versus time graph as the acceleration versus time graph. The only thing that would be different would be the values at these maximums, because you would now be multiplying by the mass. The reason the graph would look exactly the same is because mass is constant, okay? If the mass is changing, then that is going to change things up a little bit, and your graph might look a little bit different. Most of the time in AP Physics C, mass is always constant, okay? All right, so the important equation we need here is this one, because we're going to use that one again in a moment, okay? Let's talk about springs specifically. That's where we're going to start, is springs. So let's talk about oscillating springs. So for oscillating springs, the restoring force is the spring force. Okay, so if it follows Hooke's law, then that means the spring force is equal to, it's the negative times the spring constant times the displacement. I'll explain that in a second. Let me define these. This is a spring force, which is, of course, in newtons. And K is the spring constant. A lot of you on that last test did not remember that the units were a newton per each meter. You could have simply rearranged this equation to get the force divided by the displacement and literally just plugged in the units for those, and it gives you the units for the spring constant. Okay, so don't think you have to necessarily memorize those. They are there. And then X, of course, is the displacement of the spring. Okay, so when you're measuring that displacement, though, it's the stretch or the compression measured from equilibrium. Not the length of the spring, okay? So try to remember that. All right, where does the negative come in? Well, if I have a spring and I stretch it, my displacement was positive here, but the force pulls in the opposite direction. If I were to stretch my spring in the other direction, the displacement here is negative, but again, the spring pulls in the opposite direction, so it is positive. So the negative comes in here because the force and the displacement are in opposite directions. That is also how we define the restoring force. Okay, so let's talk about a couple of things that are not oscillations while we're here right now. One would be bouncing if you dropped a tennis ball and let it keep bouncing. It has periodic motion because it's repeating the up and down bouncing. It's not simple harmonic motion, though, because the gravitational force never changes direction, okay? In order to have simple harmonic motion, you have to have a force that's changing direction. So just like I talked about with the spring a second ago, how when you're stretching the spring to the right, the spring is pulling to the left. If I compress the spring to the right, the spring, or to the left, the spring pushes back to the right, okay? And that spring force is constantly changing direction to try and get that spring back to equilibrium. That's what makes it simple harmonic motion, okay? Not the necessarily just that it's going back and forth or a repeating motion. This is covered in the slideshow that I shared the link with you in the test review stuff. There's some animations in there, and if you want some visuals here, okay? All right, so the spring force. This is for an ideal spring. Ideal springs or a Hookean spring, those follow Hooke's law, okay? If we do not have an ideal spring, then we got to look at calculus, all right? The other equation is the equation for the energy, elastic potential energy, which is 1/2 of the spring constant times that displacement squared, okay? So if I have a non-ideal spring, or if I have any other kind of weirdness, so any equation they give me for the spring that doesn't look like this, I believe you had one in the last test that was something like kx squared. This requires calculus, okay? Because that does not look like the equation we usually have, all right? So the calculus piece is not necessarily written out on the equation chart, but rather it's written as the change in energy is equal to the integral of the force with respect to the displacement, okay? So we can also rewrite this in terms of the force, which would be the negative of the derivative of the energy. Oh, I missed a negative out here. The derivative of the energy with respect to displacement. Or in other words, the negative derivative of 1/2 kx squared with respect to that displacement, which just gives me the equation for the spring force, okay? This obviously was an ideal spring. That equation right here tells us that. You could also integrate the equation for the force. So if I were to do that, if I were to integrate the negative kx with respect to the displacement there, what I end up with is the change in energy is 1/2 the kx squared, which is exactly what we wrote for our equation up here. Okay, so that's how that works with the calculus. All right, so building on this, for a spring, the restoring force is the net force here, especially if we're talking about a horizontal block. That's the easier one to deal with here for this situation, because the net force is equal to the spring force. All right, so we talked about a relationship a minute ago with the acceleration, and we said the acceleration was just equal to, oops, forgot my negative in there, the negative of the angular frequency squared times the displacement. So I can rewrite my net force equation as the negative mass times angular frequency times displacement. Well, my spring force has to equal my net force. Again, we're going to get to the period of a pendulum equation from this derivation. Okay, so when it asks you to derive an equation, this is what it's asking you to do. So I have the net force is equal to mass times the angular frequency squared times the displacement. But my net force is also the spring force, so that must equal negative kx. I have negatives on both sides, so it becomes a positive. Or to not make a math mistake, let's just go ahead and do it this way. Let's divide by, we're trying to get this angular frequency by itself. So I'm going to divide both sides by the negative mass times the displacement. Now I can see my negatives become a positive. My x's reduce. So what I get is the angular frequency squared is equal to the spring constant divided by the mass. Or the angular frequency is the square root of the spring constant divided by the mass. Well, a minute ago we talked about angular frequency being 2 pi divided by the period, or 2 pi times the frequency. Doesn't really matter which way you look at it. So now I can say that the square root of the spring constant divided by m equals 2 pi over the period. I want an equation for period, so I'm going to need to multiply both sides by the period and divide both sides by the square root of k over m. And oops, apparently I can't scroll anymore. What I end up with as an equation for the period is 2 pi over the square root of k over m, or if I take the inverse of that, it's 2 pi square root of m over k, which is the equation on your equation chart for the period of a spring. Okay, so that's where that equation came from. All right, let's talk about 2 other quick things here. We're going to talk about pendulums. There are several different kinds. Actually, you know what? I'm going to go ahead and talk a little bit more about the spring, and then we'll do pendulums in the part 2 video. All right, so let's imagine I have a block here on a spring, okay? And my equilibrium position is going to be here. Equilibrium can also be thought of the rest position. It doesn't go to rest for very long, but it does have to change direction, which means it has to stop. Okay? Well, that makes this position, and you should measure from the center of the block. This is going to be my maximum positive displacement, or the maximum positive amplitude. And then it's going to go to a negative maximum amplitude. That's the same distance, okay? Let me be consistent. All right, so I have my 2 amplitudes. This area here is going to equal the distance for this area, okay? So let's say that this was a positive 2 meters and this was a negative 2 meters then. Okay, so that would, and again, this is where we're measuring ours as our 0 point. Okay, the spot right here in the middle. So this whole distance right here would be a total of 4 meters, but one oscillation would require this block to start here, go all the way over here to the maximum negative displacement, and go all the way back. So the total distance covered would be 8 meters for one oscillation. Okay, so keep that in mind. Sometimes that comes up on the test, but not very often. All right, couple other things. So if we think of force diagrams, my force diagram over here, we are assuming friction is equal to 0, okay? My spring force there is the only force acting on the block to cause it to accelerate to the left. When it gets over here to the left, the spring force pushes back to the right, and that's my only force there, okay? So at these amplitudes is where I get the maximum spring forces. That would be the maximum negative. This would be the maximum positive. But that also means this must be my maximum acceleration at these 2 positions. The equilibrium position is not where this is changing direction. This is changing direction at the maximum. So since these are the change in direction at these maximums, my velocity here is equal to 0. Okay? Because this is where I have a change in direction, are at these amplitudes. All right, so that means if those are where my maximum velocities are, we get the opposite at the equilibrium position, okay? So this is the maximum velocities here, and depending on what direction it's going, if it's going to the left, it's your maximum negative velocity. If it's going back to the right, it's your maximum positive velocity. And your acceleration equals 0 here because your spring force equals 0. Okay, at equilibrium means that we don't have a stretch or a compression of the spring. All right, since these are my maximum displacements out here at the amplitudes, all of the energy is elastic potential energy. In the middle, where I have my maximum velocity, all of my energy is equal to kinetic energy. And then everywhere in between, we have the two added together. Okay, and one quick note, kinetic energy is 1/2 mv squared. This was a question missed on the last test. Because of the square here and the square that we get for elastic potential energy, these don't have direction. Energy can't have direction. It's a scalar quantity, and we'll talk a little bit more about that in a minute, okay? All right, so this is all I'm going to talk about right now. Oh, no, I want to go back and do one more graph because I just remembered we did not do the energy graph. So let's do the energy graph really quick since we just talked about that a minute ago. If energy is conserved, that means my total energy has to stay exactly the same. So it's going to be a straight horizontal line. That's my total energy. We said that at the maximum displacements is where I have maximum elastic potential energy. So if we're referencing our graph here at the beginning, oh, it started at equilibrium on that one. Let me fix that. Oops, on here. Let me erase my little green dot here. So this graph would have to start at an elastic potential energy of 0. And then it's going to go to its maximum, and it's going to go back to 0. And then it's going to go back to that positive maximum and back to 0. Positive maximum, back to 0. Okay? Our kinetics, since at the position 0 is where our velocity is a maximum, is going to do the opposite. At the maximum amplitudes, where I have all elastic potential energy, my kinetic will be 0. And you get this dance back and forth here. So my kinetic energy graph is going to be curved like this, and my elastic potential energy graph is going to be curved in the opposite direction, okay? But everywhere, the total energy has to be the two of them added together. But when elastic potential energy is 0, all of the energy is kinetic. When the kinetic energy is 0, all of the energy is elastic potential energy. Okay, the next video I will talk about pendulums.